The topic of today's video will be evaluation of integral of this type, minus infinity to infinity, and the integrand is a rational function px over qx, right? So before starting how to evaluate this integral with the help of that residue theory, I will start some basic concepts of this improper integral, right? Okay. If fx is a continuous function in interval 0 to infinity, right? Then capital I is equal to integral 0 to infinity fx dx is actually equal to, in order to evaluate this improper integral, why we are saying it improper, because the upper limit is infinity, right? It can be evaluated by writing limit r tends to infinity 0 to capital R fx dx. This is how we evaluate an integral of this form, right? We say that integral I, this integral, converges if the right hand side, the integral on the right hand side exists finitely. It means that we say that this integral capital I converges if this value, the right hand side integral, has some finite value. Okay. Similarly, if f is a continuous function in the whole real line, right, then I equal to integral minus infinity to infinity fx dx is evaluated by breaking this integral into two parts. The first is minus infinity to 0 fx dx plus 0 to infinity fx dx, right? And for each part you can write limit r1 tends to infinity minus r1 to 0 fx dx plus limit r2 tends to infinity integral 0 to capital R2 fx dx, right? It means that the problem of evaluating this integral where the limits are from minus infinity to plus infinity is actually equal to the sum of evaluating these two integrals, right? And we say that this capital I converges, we say that integral capital I, the integral on the left hand side, converges if both the integrals on right hand side exist, right? Means the convergence of this integral depends on the existence of these two integrals. They should exist finitely so that their sum will exist, and we will say that this integral converges, right? So these are the facts you already know from the theory of real calculus, right? Now the new thing is that a new thing is Cauchy principal value, right? I will write that here. Cauchy principal value of an integral of this nature, right? So it is defined as we write PV, principal value of the integral of this nature with the limits from minus infinity to plus infinity fx dx equal to limit capital R tends to infinity minus r to capital R fx dx, right? And obviously this right hand side is not the same as this one, right? It appears that these two are equal, but they are not equal actually. They may be equal in some cases. So this is defined as a principal value of an improper integral which has limits minus infinity to infinity, right? So how this Cauchy principal value is related to this already known value of integral, improper integral, I will write that point. If should I write at remark integral minus infinity to plus infinity fx dx converges, right, implies that principal value of this thing minus infinity to infinity fx dx exists, right? So whenever this improper integral converges, right, then principal value of this integral always exists, right? But the converse is not true, right? And whenever this happens, I can write here, this further implies, I will write it here, this further implies that these two integrals will be equal, right? I should name them A and this integral as B, right? And if this whole condition is true, then we say that the integrals are also equal, right? So whenever you have a converging integral like this one, then the principal value of that integral will always exist, and as well as the two values of the integral will always be equal, right? But the converse is not true in general, right? But whenever principal value of such improper integral exists, right, it does not imply that integral minus infinity to infinity fx dx converges, right? The converse is not true. Okay, so I will put a box here in order to highlight this condition, which does not hold every time. Okay, now I should write it condition number 1, right? Condition number 1. So I will come to Cauchy principal value, how it is evaluated. I will take a small example or maybe a supporting example to prove this fact, right? I will take an integral such that its principal value exists, but the integral does not converge, right? We should take an example, and to prove this, first I will take, for example, if I take if fx equal to x, right, and you can see that this function is continuous inside this domain minus infinity to infinity. The first thing is that, and then you will evaluate its principal value of this integral minus infinity to infinity x dx, and remember that the principal value is evaluated by using this fact, not by breaking this integral into two parts as we did here, right? So in order to evaluate its principal value, just use this, right? Okay, so limit r tends to infinity minus r to capital R x dx, right? And then on integrating it, I will get limit r tends to infinity, integration will give you x square over 2, and on plugging limits, r square by 2 minus r square by 2, and you can see that these both terms will cancel and the answer will be 0, right? It indicates that the principal value of this integral is equal to 0, right? But the actual value of this integral doesn't exist, because this integral actually doesn't exist. It doesn't converge, right? But if you find its value by using this rule, by breaking into two domains x dx, I should write here x dx plus 0 to infinity x dx. I am using this rule this time, and then writing limit r1 tends to infinity, and here I will have minus r1 to 0 x dx plus limit r2 tends to infinity 0 to r x dx, and you will integrate it, you will get x square by 2, or limit r1 tends to infinity, you will get minus r1 square by 2, right? And I think negative sign will be there because x square by 2, this is a lower limit, so we will have minus sign here, and there is no need to write this minus because negative minus 1 square is equal to plus 1. And for this we will have limit r2 tends to infinity r square by 2, right? And since this limit doesn't exist, so we cannot say that this integral converge, because if you see here that we say that this integral converges if both of them exist, and we can see that both of these limits are not existing, they are approaching to infinity. If you plug r1 tends to infinity, you will get infinity square. It means that this integral actually doesn't converge, but we are having a principal value of this integral, and that is equal to 0, right? So this is a supporting example to prove this first condition, when this principal value exists, but we cannot say that the integral converges, right? Okay, but what happens when this fx is an even function? I have taken an example of an odd function. If I take fx equal to x square, then this then this condition still hold, means we have integral exist implies this principal value exists and integral converges, right? So I will write a new heading for this, means the case when this condition holds, right? So when does this condition PV, principal value of minus infinity to infinity, fx dx implies minus infinity to infinity fx dx converges, right? Holds. The question is that you have to find the situation when this reverse condition, means the converse of this thing, hold, right? And this is my heading. Okay, if fx is an even function, right, then principal value of minus infinity to infinity fx dx exists. I should write exist here, implies minus infinity to infinity fx dx converges, right? Means the converse of this remark holds whenever you have fx as an even function, right? And we have a small proof for this proof. Since we are claiming that f is an even function, it means that if fx is an even function, then f of minus x will be equal to fx, and for the graph of fx, it will be symmetrical about the y-axis, right? You can think of any even function, like you have y is equal to fx equal to x square, and if you plot its graph, it will be a parabola looking like this, right? And you can see that the graph is symmetrical about the y-axis, right? And in that case, the area of the left half is equal to the area of the right half. If a graph is symmetrical about the y-axis, obviously the two area in both halves will be equal, right? Or we can say that the area in the right half is equal to the area of the left half is further equal to the half of the area of the whole real line, right? Okay, I will use that logic. Since fx is even, hence the curve, the graph of fx is symmetrical about y-axis, right? And you should know the reason why I'm writing that. Think of any even function and draw its graph. It will be symmetrical about y-axis. Like y is equal to x square is the simplest example. Okay. Obviously, in that case, the area, and why I'm saying that it is area, actually if y is equal to fx is the curve, then this definite integral means you have the limits from x1 to x2, and fx dx, it represents the area of the curve above x-axis, right, below the graph and above the x-axis within the limits x1 to x2. So actually it represents the area, right, of the left hand side is equal to the half of the total area, right. I should write minus r1 to r1 fx dx, right. This fact is very simple. You just take 2 points. Here it is minus r1, here we have r1, this is a y-axis, right, and you have a graph which is symmetrical about y-axis, right. So it will be like this one, right. So obviously the area of the left half is equal to the area of the right half because the graph is symmetrical, and each area, the left hand side area and right hand side area, is equal to half of the whole area, right. So this is the fact we have represented in terms of an equation, okay. And if I write 0 to r2, this is for the right hand side, right, 0 to r2 fx dx should be equal to half of minus r2 to plus r2 fx dx, right. So if I add them, this first and second, first plus second, we'll get minus r1 to 0 fx dx plus 0 to r2 fx dx equal to half minus r1 fx dx plus half minus r2 fx dx, right. Okay, since we are interested in this integral with the limits minus infinity to plus infinity, so I will approach r1 to infinity and r2 to infinity in order to achieve this thing, right, as r1 tends to infinity and r2 tends to infinity, right. Then I will get minus infinity to 0 fx dx plus 0 to infinity fx equal to limit r tends to infinity minus r to r fx dx, right. You can see that since r1 is equal to r2, sorry, r1 and r2 both tends to infinity, or you can write r1 and r2 can be treated as r and limit is approaching to infinity, so the right hand side can be written this way, right. And this is obviously the Cauchy principal value. If you see from here, right, this is the principal value of fx dx, and this is the actual value of the integral. You can see from here, right. So that will give me minus infinity to infinity fx dx is equal to principal value of minus infinity to infinity fx dx, right. So this is a small proof for this, right. And yeah, they both are equal, and I should write it here. Whenever this implies this, obviously both of them are equal, right. So we can say that when fx is an even function, then this implication, for this implication, the converse part is also true, right. And yes, to evaluate an integral of this type, we'll use our residue theory. What we'll do, we'll replace this real integral by complex integral, and when we replace an integral by a complex integral, we need some contour, right, and then we have to use that Cauchy residue theorem as we used in our last video, right. So I will start with the first I will give a small method how to evaluate this type of integral, right, and then I will take some examples. So how to evaluate integral minus infinity to infinity px over qx dx, right. Okay, the first important point is that this function, this is a rational function, px and qx are polynomials, and they don't have common zero, right, means they don't have common factors. First thing is that, and this function, rational function, should be continuous inside this interval minus infinity to infinity, right? Okay. Then what we do, we consider an integral that is C, it should be closed C, and Pz over Qz dz, right? So rather than evaluating this real integral, we first go to complex integral and we replace this x by z, and where C is a contour, and C is where C is the contour consisting of interval minus r to capital R, right, and a semicircle CR, right, in the upper half plane, right, with radius R large enough to enclose all poles of Pz over Qz in the upper half plane. Okay, so we replace this integral by this complex integral where C is the contour, and the contour is of this nature. You can see that the real interval minus R to R, this is on the real axis, minus R to R, right, means this part, and with a semicircle CR, right, like this. So this is our contour, and this portion, the semicircular arc, is denoted by C capital R, right, and this interval is minus R to R. So our contour is this. This is your whole contour C, contour C, contour C, right. And what about the radius of this semicircle? It should be large enough. R should be large enough to enclose all the poles of this function, right? Suppose you have poles Z1, here is a pole Z1, this is a pole Z2, and there are so many poles up to Zk. You have to draw a semicircle bigger enough in order to enclose all of these poles which lie in the upper half plane, right? You are not worried about the poles which are lying in the lower half. You are only interested to enclose all the poles that lie in the upper half of Z plane, right? So this is the basic idea in order to evaluate this integral, right? And now, since we have this integral, right, we will apply residue theory here. We will find the poles of this function, right, and we will be interested in finding the residue at poles which lie in this contour, right, and after finding residues, we will apply that Cauchy Residue Theorem, right. I will write that. Then the value of this integral C Pz over Qz dz is equal to actually you can see that this contour C, the whole contour C, is actually union of two curves. First is the real interval, and then is the semicircular arc, right. So I will break this C in two parts. First is minus R to R, this part, and here since the function is defined on the real axis, so you will write Px over Qx, right. And for this semicircular arc, and again you see that the orientation is anti-clockwise, that is considered as positive, right. So you write CR here and Pz over Qz dz, right. Okay, and yes, if I approach R tends to infinity, then it will become minus infinity to infinity, and this integral goes to 0, right. We will show that in numericals how it goes to 0, but I will write that here as r tends to infinity, right? The left hand side integral is equal to limit minus infinity to infinity px d px over qx dx, and you can see that when we write limit r tends to infinity here, then we write minus infinity to infinity. It means that this is principal value, right? Plus this integral goes to 0. I should write it here, cr pz over qz dz goes to 0, especially this part. How it goes to 0, we'll show that in numericals, right? So ultimately the real integral, this was our target, right, is actually equal to the contour integration of this rational function over this specially designed contour, the semicircle, right? So this is the theory about this, how to evaluate an integral of this type. I will take examples. Okay. Example number 1, find the value of integral minus infinity to infinity dx over x square plus 1 and x square plus 9, right? So we can see that the function integrand, that is px over qx, is a rational function. The px is actually equal to 1 here, and qx is actually equal to the product of x square plus 1 and x square plus 9, right? So we have to evaluate this integral. You can see that this is a real integral, but we will use the residue theory in order to evaluate this. And before doing that, I have to consider a corresponding integral, which is a complex integral, right? You see here, you just replace the z, x by z, and you put c here, and you c is defined in this way, semicircle together with this diameter, right? So I will start like my theory. Consider I is equal to, I will name that integral I is equal to the integral, complex integral with the contour c. When you talk about the complex integral, you talk about contour, right? That's obvious. Dz over z square plus 1 and z square plus 9, and you have to define what is your c, where c is, I'm not writing the whole thing, right? I'm just drawing the figure where c is as shown in figure, right? You should write the whole thing. Okay. This is my contour, minus r to r, and then the big semicircle, bigger enough to enclose all poles lying in the upper half plane only. Okay. This is the direction. This is minus r to r, and we call it cr. This part is called cr, and the whole thing is called c. It means that c is actually a union of this interval and the upper semicircle, right? And now I will use this theory. I'll focus on this, right? If you focus on this complex integral, you will see that the poles will be given by, poles are given by putting denominator equal to 0, and that will give you z equal to plus minus iota and plus minus 3 iota, right? So we have, and they all are simple poles, right? And why I'm calling them simple, because you can see that they are obtained with multiplicity equal to 1, and whenever we have a rational function, the multiplicity of the pole is actually equal to the order of the pole, right? Or you can also check it by differentiating the denominator again. Okay, so iota and 3 iota, here I will have iota on my y-axis, this is iota, and this will be 3 iota, right? So your circle, semicircle, should be large enough to enclose both these poles, right? Whatever is the pole, wherever is its position in the upper half plane, your circle, your semicircle always must enclose all of the poles lying in the upper half plane. That is the basic requirement to use this theory. Okay, so clearly our two poles, iota and 3 iota, lies within C, right? Okay, and I will evaluate a residue at these two poles, and both of them are simple poles, right? Simple poles, right? So residue of function fz This is the fz whole function, right? This one evaluated at z equal to iota is equal to limit z tends to iota and z minus iota multiplied by fz. This is fz. The whole function is fz. Okay, where fz is 1 over z square plus 1 and z square plus 9, right? And when you multiply this z minus iota with fz, this z square plus 1 is actually equal to z plus iota and z minus iota. So z minus iota will be cancelled out. You will be left with z plus iota and z square plus 9, right? And then you will put your z equal to iota in this, z square plus 9, and then you will put limit z tends to iota and you get 2 iota, and this will become 8. So ultimately you will be having 16 iota, right? 1 over 16 iota. And similarly, residue of fz at z equal to second pole, which lies inside this contour, that is 3 iota. Limit z tends to 3 iota, z minus 3 iota multiplied by fz, and your fz is this. So you will get I think limit z tends to 3 iota 1 over z square plus 1 and z plus 3 iota, right? And on putting 3 iota, we will get 6 iota from here, and this will be minus 9 minus 8. So minus 8 into 6 iota, right? It will be minus 1 over 48 iota, I think, right? Okay, then I will use residue theorem. Using residue theorem, and that is actually the contour integration of dz over z square plus 1 z square plus 9 should be equal to 2 pi iota times the sum of residues, right? And I should write here residue of fz evaluated at iota plus residue of fz evaluated at 3 iota, right? And on adding these two residues, I will get I think 3 minus 1 2 by 48, I think 1 by 24, yeah, 1 by 24 iota, 1 by 24 iota, and here I will have 2 pi iota, so I'll get pi by 12. So pi by 12 is the value of this complex integral, and do not forget that we are focusing to evaluate a real integral, right? And I will come to that. This is the value of my I integral, right? Now I will use this equation, this one, right? And we have to show that this goes to 0. Now see dz over z square plus 1 z square plus 9 equal to minus r to r dx over x square plus 1 x square plus 9 plus cr dz over z square plus 1 z square plus 9, right? It is from figure. From figure you can write this, right? The evaluation of the integral I over the whole contour is actually equal to the sum of integrals evaluated over this part of real line plus the function, the integrand evaluated along this CR, right? So this is obvious from the figure, and I will plug the value of this thing, and this is actually equal to how much? Pi by 12, or pi by 12 is equal to minus r to r dx over x square plus 1 and x square plus 9 and plus this integral CR dz over z square plus 1 and z square plus 9, right? So as r tends to infinity, right? You will get pi by 12 equal to minus infinity to infinity, right? dx over x square plus 1 x square plus 9, right? And this is obviously principal value, right? Okay, plus this will go to 0, right? 0, right? And the reason for this is here why it is 0, right? As I am talking about this small integral, as dz over z square plus 1 z square plus 9, if I take the modulus of this thing, right? I am taking an estimate, the modulus of this thing, that should be less than or equal to dz mod dz over mod of z square plus 1 and mod of z square plus 9, right? Okay, and you can see that, see the denominator, this is z square plus 1. If you want that this whole integral, you have something here which is bigger than this, right? So to do that, you have to squeeze this denominator. If you write a smaller denominator here, then this whole integral will be bigger than this one, right? Okay, so I'm trying to diminish the denominator, and that is actually equal to mod z square minus 1, right? That's simple, because I am replacing plus 1 by minus 1. Obviously this is smaller than this one, and ultimately the whole term will be bigger than the previous one, right? And similarly for this one, mod z square minus 9, right? I have used here the inequality. You should know that mod of z1 plus z2 is greater than or equal to mod of mod z1 minus mod z2, right? I will write that. First I will complete this, right? Okay, as, and you can see that this is a semicircle with radius equal to capital R. So its equation will be mod z equal to capital R and theta varying from 0 to pi only, right? Okay, as I should write it I1, right? As I1, mod of I1 equal to, I should write I1, right? And let it be equation number I1, say let it be equation number 1, right? Okay, so I'm evaluating the value of I1, okay, up to this point. Now C is mod z equal to R. You can see that your contour C is a semicircle together with this diameter, and we are evaluating this on CR. Sorry, CR. It should be written here CR, right? CR. So here CR is, if you focus on the semicircle part only, this is actually a semicircle or a part of circle belonging to the upper half plane, and that should be written as theta belonging to 0 to pi, right? So this is a nice way to represent a semicircle in the upper half plane. Okay, so I will replace mod z by R here, right? So that will give me, therefore, mod I1 less than this thing. First I will write the denominator part. This is R square minus 1, and this will be R square minus 9. And what about this integral of mod dz? That will be the length of this semicircle, right? And that is actually equal to the perimeter of semicircle, that is equal to pi r, pi times the radius of circle. So pi times the radius of circle, right? And I should write here limit r tends to infinity here plus limit r tends to infinity, right? Now I will apply r tends to infinity, right? And should I write it here? It will go to 0, right, as r tends to infinity. Why? See here, the numerator is having r to the power 1 and the denominator is having r to the power 4, right? So denominator is much bigger than the numerator, or you can apply that limit rule, or you can use that LH rule, L Hospital's rule. You will get 0 as r tends to infinity, right? You should divide this by r to the power 4 in the numerator and denominator, and then on approaching r tends to infinity, you will get 0, right? So we can say that I1 is equal to 0 because this is a positive quantity, and the positive quantity is less than 0. Obviously, it will be equal to 0. I should put a equal here. I think I1 equal to 0, right? Limit r tends to infinity. So I will plug this value here in my equation number 1. Therefore, equation 1 will give me a principal value of minus infinity to infinity dx over x square plus 1 and x square plus 9 is equal to pi over 12 because it is equal to 0, right? But since this is an even function, you can see that this is an even function, all even powers of x occur here. So we can say that the principal value is actually equal to the value of the integral whenever we have an even function, right? Since fx is even function, therefore the value of the actual integral is equal to the principal value of the integral, all right? That is equal to pi over 12, right? So the proof of this goes like this, right? I will take another example, and before that I have to rub this board. Take another example. Example number 2. Find the value of integral 0 to infinity x square dx upon x to the power 6 plus 1, right? This time I have taken limits from 0 to infinity, right? Okay. And yeah, the procedure is similar. I have to start with this integral, then I will use some even and odd function theory, right? Solution. You should start with the same thing. Consider an integral I similar to this one, but this x is replaced by z, so you will have this thing, right? And where c is what we have described earlier, right? Where c is as shown in figure, right? The radius of this semicircle should be large enough to enclose all the poles in the upper half plane, right? And the whole contour is actually the union of this interval and this CR, right? This is the whole contour, okay? And you find its poles, right? Its poles will be given by equating this to equal to 0, and you will get, I think, z to the power 6 z equal to, I should add the poles directly. We have done this in previous videos, and that should be e to the power minus 1. That is a cos odd multiple of pi, and cos 0, 2n plus 1 pi. Okay, that will give you z equal to e to the power eta 2n plus 1 pi by 6, if I am not wrong. Yes, minus 1, and cos is negative for odd values, odd multiples of pi, okay, where n equal to 0, 1, 2, 3, 4, 5, right? Okay, then that is, I will write all the poles, plugging 0 here. I will get e to the power eta pi by 6, and e to the power eta putting 1 here, 3 pi by 6, that will be pi by 2, and e to the power eta putting 2 here, 5 pi by 6, and e to the power eta putting 3 here, 7 pi by 6, then I think 4 here, 9 pi by 6, that will be 3 pi by 2, 3 pi by 2, and the last will be e to the power eta putting 5, 11 pi by 6, right? And if you plot all of these poles here in this semicircle, this e to the power eta pi by 6, this angle indicates that it is a 30-degree angle, and its modulus is equal to 1. It indicates that actually this point will belong to the circumference of a unit circle at an angle of 30 degree. So it will be somewhere here. This z1 e to the power eta pi by 6, and e to the power eta pi by 2 will be here, e to the power eta pi by 2, and the third one will be e to the power 5, e to the power eta 5 pi by 6, and the rest of these three poles will not belong to our contour, right? Only these three will qualify, and all of them are simple poles, right? Okay, only e to the power iota pi by 6, e to the power iota pi by 2, e to the power iota 5 pi by 6 belong to C, inside of C, belong to inside of contour C, right? So I will find a residue at each of these poles, residue of Fz at the first pole e to the power iota pi by 6, and since each of them are simple poles, so I can use the differentiation formula also. The numerator is written as it is, and differentiate the denominator, I will get 6z to the power 5, so ultimately it will become 6z to the power 3, yes, and then I will put this pole z equal to iota e to the power iota pi by 6. I think it should be taken in the numerator. That will become 1 by 6 and z to the power minus 3 and e to the power minus iota pi by 2 after cancellation, right? And on writing its full value, cos 90 is 0 minus, so minus iota by 6. This is the value of the residue, right? And the second residue evaluated at e to the power iota pi by 2, that will produce from here 1 by 6 z to the power minus 3 and z equal to e to the power iota pi by 2, right? And if I plug here, it will get e to the power minus iota 3 pi by 2, I think. Yes, and that will be sine 90, obviously, minus, that will produce iota by 6, iota by 6, right? Because sine 3 pi by 2 is minus 1. Okay, and third one, residue of Fz at e to the power, third is 5 iota 5 pi by 6 is equal to 1 over 6 z cube, z equal to e to the power iota 5 pi by 6, and that will produce 1 by 6 e to the power minus iota 5 pi by 2, and 5 pi by 2 is actually at the same place where you have pi by 2, so it will be cos 90 0 sin 91 minus iota by 6, right? Okay. So adding these residues to get the value of I, therefore I equal to 2 pi iota, and sum of these residues, you can see that you will get minus iota pi by 6 ultimately, and you will have, I think, pi by 3, yeah, pi by 3, iota square minus 1, fine. So we'll have pi by 3 as the value of this complex integral, right? But we have to evaluate this real integral, and again we have to use that procedure from figure. From figure, you can see that your I, the whole complex integral, is actually equal to the union of two integrals, that is x square dx over x to the power 6 plus 1, and then this semicircle contour z square dz over z to the power 6 plus 1, right? And similar to that one, I will plug the value of I is actually pi by 3, or pi by 3 equal to, should I approach r tends to infinity? Okay, as r tends to infinity, you will have this thing, okay, and this will become principal value of minus infinity to infinity x square dx over x to the power 6 plus 1, and let me call it I1, right? Say, and this is my equation number 1, and now I will show that this I1 approaches to 0 as r1 tends to infinity, right? This is my first equation, and now I will show that now mod of I1 is equal to mod of integral evaluated along CR z square dz over z to the power 6 plus 1, right? So it will be less than or equal to CR mod z square mod dz over mod of z to the power 6 plus 1, right? And now we'll squeeze this denominator, right? In order to squeeze this denominator, I will write CR mod, and it is replaced by, okay, first I will write that mod z square dz, and it will become mod z to the power 6 minus 1, like this, right? And as now CR is actually mod z equal to r. You can again see that the contour is mod z equal to r, the upper semicircle, right? And theta 0 to pi, right? Because the semicircle is belonging to the upper half, right? Okay, and note that this is CR, this is not C. C is actually the semicircle plus diameter, but we are talking about the semicircular arc only. That's why I have written CR only, right? So be careful at this point. Okay, so I will plug this here, or should I write since? Okay, that will give me therefore mod I1 less than or equal to, it should be equal to r square and integral of this dz, right? That will be the length of this semicircular arc, and that is equal to pi r over r to the power 6 minus 1. And you can again see that the denominator is having 6 power and the numerator is r cube. So ultimately the denominator is big, so that will go to 0 as r tends to infinity, right? So you can write that limit r tends to infinity I1 equal to 0, right? So I will plug this value here in my equation. Therefore equation number 1 becomes principal value of minus infinity to infinity x square dx over x to the power 6 plus 1 is equal to pi over how much? 3, and that is plus 0, right? Plus 0, okay, fine. But the original integral was 0 to infinity, not this minus infinity to infinity, right? First I will use that concept. Since fx is even function, you can see that this is an even function, odd even powers of x occur in this integrand. So since fx is even, principal value is actually equal to the value of the integral, right? Is equal to pi by 3, right? Now again, since fx is even, we can also write twice 0 to infinity x square dx over x to the power 6 plus 1 equal to pi by 3, right? As fx is even, since it is an even function, using the same property minus a to a, when limits are minus a to a fx dx, that can be written as twice of integral 0 to a fx dx, right? So ultimately bringing this to here, right, I will get pi by 6. Okay, now taking my last example, maybe for the case when this is not an even function. So far we have done 2 examples, both of these were containing an even function, right? So this time I will take a function which is not an even function. So obviously I will not talk about its value, rather I will say the principal value, right? Whenever we have an even function as an integrand, the principal value of the integral and the value of the integral are same, right? But whenever we don't have an even function, right, we cannot say that the value of the integral is equal to principal value, right? So I will be taking an example of non-even function, right? Example number 3, find the principal value of integral. Should I take minus infinity to plus infinity? Okay, and here I will take x square dx and x square plus 1 whole square. This is fine. Up to this point it is an even function, right? and in order to get an odd function I should write some terms containing x also, like this. What happens if I remove this? Okay, square. Simple pole. I want to get simple pole. I don't want to use that derivative formula. Okay, so solution. Again I will start with the same integral. Consider I equal to integral c z square dz over z square plus 1 and z square plus 2z plus 2, where c is as shown in figure, right? And that is obviously a semicircle, right? Minus r to r, and the upper semicircle is CR, right? And you can see that the poles of this function will be plus and minus iota from here, and from here I have to find the poles, right? Poles are given by, I think if I equate this to 0 I will get z equal to plus minus iota. That is simple. And if I equate this to 0 I will get minus 2 plus minus 4 b square, 4 minus 8, I think minus 4, and that will be 2 iota. Okay, I think minus 1 plus minus iota, minus 1 plus minus iota, if I'm not wrong. Yes. B square 4 minus 8 minus 4, yeah, 2 minus 1 plus minus iota. Okay, and all of them are simple poles, right? And only 2 of them will qualify. The first is iota. Iota will be here, I think, iota, and minus 1 plus iota, minus 1 plus iota, that will be minus 1 plus iota, that will be in the upper half plane also, right? The height is iota here, minus 1 plus iota. So only 2 poles will qualify, right? Okay, only z equal to iota and minus 1 plus iota belong to inside of contour C. And remember that our contour C is actually the union of 2 curves. First is the interval from minus r to r, and the another is the big semicircle, bigger enough to enclose all the poles that lie in the upper half plane. I am not writing that again and again. You have to write that. You have mentioned at this point where C is the contour consisting of this interval minus r to r and the big semicircle CR, right? Bigger enough to enclose all the poles in the upper half plane. You have to write that line. Okay, belong to C. Now I will find residues at these points. So residue of fz at the point pole iota, right? This is a simple pole, and where is that function? Okay, and this is a simple pole. So z minus iota will be cancelled out. I'll plug iota square. I will have iota square, that is actually equal to minus 1 over z minus iota, z plus iota, that will be cancelled, iota plus 2 iota, and it will become iota square minus 1. So minus 1 plus 2 iota plus 2, I think it will become 1 plus 2 iota. So minus 1 over 2 iota, 1 plus 2 iota, right? And should I multiply it? Okay, not needed actually, right? Okay, and residue at the other pole, minus 1 plus iota, and this will be, okay, I have to write the limit z tend to, should I differentiate it? Okay, I will factorize it rather. Z tends to minus 1 plus iota and z plus 1 minus iota multiplied by z square over z square plus 1, and I will factorize this because it is containing this factor, right? We should factorize this. It is z minus, where is those pole, where z minus, z minus first pole. The first pole is minus 1 plus iota, z plus 1 minus iota, and the second pole is minus 1 minus iota, so it will be z plus 1 plus iota, right? If I'm not wrong. Right. And then this will be cancelled, right? And then you will put z equal to this much here. So we'll get minus 1 plus iota whole square and here in the denominator you will get minus 1 plus iota whole square plus 1, and here minus 1 plus iota, so I think 2 iota, and on opening it I will get 1 minus 1 minus 2 iota, minus 2 iota, minus 2 iota, and on opening it I will get 1 minus 2 iota, 1 minus 2 iota, and 2 iota, and ultimately we will get minus 1 over 1 minus 2 iota, and I was getting this thing here. Okay, now I will write therefore I equal to, using residue theorem, 2 pi iota multiplied by the sum of residues, right, minus 1 over 2 iota, 1 plus 2 iota, and this is minus 1 over 1 minus 2 iota, right. Okay, should I take the LCM? If I take the LCM I will get to 2 iota, and 2 iota will be cancelled out. No, not now. 2 pi iota is outside, and here I will have 2 iota. 1 square minus 2 iota square, that will be 1 plus 5, 1 plus 4, that will be I think 5. Okay, so ultimately it will become 5. On multiplying these two, it will go here. I will get minus 1 plus 2 iota, right, minus, it will become 2 iota and plus 4 iota square, or minus 4 iota square, or plus 4, right. Now this 2 iota will be cancelled. 4 minus 1 is 3, so ultimately 2 iota will be cancelled. 3 pi over 5, if I am not wrong, 4 3 and 2 iota cancel, yeah, 3 pi by 5. Am I correct? Okay, 3 pi by 5. And now I will use that logic again. From figure you can see that integral, contour integral with the function z square dz over z square plus 1 and z square plus 2z plus 2 is actually equal to the sum of two integrals, the real one, x square dx over x square plus 1, x square plus 2x plus 2, and plus cr z square dz over z square plus 1, z square plus 2z plus 2, right. And again using the same logic, this integral will go to 0. You will show it yourself, right, as r tends to infinity. You will get the value of this integral is 3 pi by 5, 3 pi by 5, and this will be principal value of minus infinity to infinity, x square dx over x square plus 1, x square plus 2x plus 2, and this will go to 0, right. You should write it y, right. So ultimately this will be the value of the integral, right. This is it for this video. The next video will be doing something more on the evaluation of integral, maybe of the different type. That will be part of the next video. For this video, thanks.